Hi everyone, this is going to be our note for 7.6. We're going to be looking at the exponential growth equation, and this is kind of in two parts. There are two handouts for it. The first part we're actually going to do a proof to see how do we get this equation, and then we're going to start applying this equation to some real life examples. So an example of an exponential growth problem is here. A biologist grows a colony of bacteria in a petri dish and finds that after 1 day the quantity has increased by 50%. After 2 days, it is increased again by 50% of the quantity noted after day 1. The biologist is uncertain as to the exact initial number of bacteria. Determine an algebraic formula that can be used to describe the quantity after 10 days and then after n days, meaning we can apply any number of days and we can kind of figure out the population. Sorry, I just wanted to zoom in a little bit and then I'll kind of reveal our proof as we go along. We don't remember how much the exact initial number of bacteria was, so we're going to let this variable PO represent the initial number of bacteria. And then we're going to break this down into percentages. Now, as we go through this, we might just want to assign a number to this, just kind of to help us visualize. So let's just maybe add, make this equal to 100, and then we can see this as we go along. So after 1 day, they say the population of the bacteria increases by 50%. So it's like my original population, 100% of that, all of that, because they're still there, and then another 50% of that initial population. So if you think about it, if we had to put our number to this, it's like if I have 100% of our population, which is 100, like this is the total population, it will be our initial population plus 50% of the initial population. Because we haven't lost anyone, we're just adding more to our initial population. So we start with 100, and we're going to add to that 50% of that to that. Now, just by looking at some algebra here and just looking at the variables, notice that we have this common factor here. So I'm going to factor out PO here, or the initial population. I'm going to factor that out so that I just have these two percentages inside the brackets here. So PO is equal to 100% plus 50%. And since this is after 1 day, we're going to call this P1. So this is just after 1 day. After 1 day, the population increased by 50%. And if I look at my numbers here and I did that calculation, and actually I follow this, where our initial population we said was 100, and then I have 100% plus 50%, which is really 100 times 150%. And if I turn that to a decimal, I get 1.5. 100 times 1.5 is going to give me 150, which makes sense. If I started with 100, and I know it increases by 50% every day, increases by half every day, I'm going to get 150 here. So then what happens after day 2? Well, day 2, we're looking at our 150 here, and now this is our P1. So that's what would go here for P1, because we have this new population, which incorporated the 50% from the first day. So we're going to get 100% of that plus 50% of that population as well. And then I'm just doing the same thing again. I'm going to common factor this population after day 1, and then I have 100% plus 50%, and that's going to equal the population on day 2. So if I did this again, I would get 100% times 150 plus 50% of 150, because I'm always adding, increasing by 50% every day. So I do this calculation and I'm going to get P2. So then if I simplify this and I look at what I have answered here to get these variables, on day 2 we said it's the day 1 population here, this equation here. So like this part is what's here. So the day 1 population is 100% plus 50%. Well, what did we say the day 1 population was? Well, the day 1 population is here. We said that's equal to the initial population times 100% plus 50%. So we got this part of this equation, and we moved it over here. So now it takes up this spot. So by manipulating this, now we can see it's just our initial population times 100% plus 50% in brackets, and then times this again. So because it's the same thing multiplying together, this is just squared. So 100% plus 50% squared times the initial population. So this is for day 2. So we can kind of figure out what's going to happen if I keep doing this. We see that after 2 days, our exponent here is 2, where 0.5 is the growth rate, because that's how much increasing by percent-wise every day. So after 10 days, you can expect the exponent here to be 10, and after n days, it's going to be the exponent n, where n can be any number of days based on this situation. So this equation is called our exponential growth and can be bundled by this formula, where Pn is the final amount that we were looking for. Po here, our variable here, is the initial amount that we said. The r is the growth rate, represented as a decimal or a fraction, not as a percentage. And n is the number of growth periods, which is the exponent here. So just to add to this little bit here, I don't want to say just because the day here is here, therefore the exponent is here. It just means it just happens to match up. That if I did it for P3, for day 3, I'll do it like this. It would be P0 and then 100% plus 50%. And this would happen 3 times. One for each previous day. Or for each, yeah. So then it would just be to the power of 3. So it just keeps occurring again and again and again, and that's how we get it to be the exponent here. So before we get to the second part, I want to look back at our problem that we had in 7.5 of $1 million cash, or you get a cent a day for the first day. And if you remember the note for 7.5, we had our equation to be, I think we said total, but I think it was just 0.01 to the power of n, and we'll just say like total t. So how did we get this? Well, remember, equation that we just learned is this. So in this case, our initial amount for this question is 0.01. That's how much we start with, 1 cent for the first day, and then it doubles each day for 31 days. So this is going to be 0.01. And how much are you getting? You're getting double the amount each day. So your amount plus 100% of that. So your rate every day is you're getting 100% of what you have every day. You just double it. So we're adding 1.00 here to the power of n, which if I simplify that, this and this, I just get 2 here. So that's why we have our doubling. So yeah, this is just how we got this. Okay, now that we have that equation, we're going to be seeing this in many different scenarios here. We often see it in fields of science and finance. We see this when describing the growth of bacterial culture, like we saw in the very first example. We can use to calculate compound interest and determine population growth. So for exponential growth, just a quick recap, its function this, where b is greater than 1, and this is called an increasing function. And we have a, which represented that vertical stretch or compression. A couple notes to remember: the value of a is the y-intercept, because we want to find the y-intercept. Remember, y-intercept x is equal to 0, and if I have my function here, and I set x equal to 0, x is the exponent. Anything to the exponent 0 is 1. A times 1 is just a. So we can also use this as an initial value for functions whose domain is when x is greater than or equal to 0. So just that can help us out in some of these questions. And then we went over this equation, exponential growth. It's in this note as well. And just a note at the bottom here, units for the growth rate and the number of growth periods must be the same. So for example, if the growth rate is given as per hour, the number of growth periods in the equation must be measured also in hours. Okay, so some examples. Example 1, the population in a small town is predicted to grow at a rate of 8% per year. Currently, there are 25,234 people in town. Determine a formula to calculate the projected population in 20 years. So I'm going to write out a formula for growth. 1 plus r to the power of n. Our rate is per year, so r is 8%. Remember, it has to be a decimal or a fraction. So we're going to use a decimal as 0.08, which is just 8 divided by 100 to get this. Then we have our initial population is 25,234. And we need at least one other variable, and they tell us a projected population for 20 years. So n is going to be 20. So my formula would be the population after, well, I guess n we're saying is 20 years is 25,234 times 1 plus 0.08 to the power of 20. Then we can simplify this a bit. We can actually solve for it if we want to. 234. So doing this quick, I get 25,234 times 4.66 times this, and I get 117,614.59. So to be safe, let's just round this up to a whole number. So that would be a projected population in 20 years. Now, this is just, again, a projected population because there are many other factors that can affect population. Maybe there's just a lot of people just moving in more than you would think in one particular year. Maybe there's a lot of people leaving one particular year, but if we're just maybe projecting growth where it could happen, then we can just estimate it using an equation like this. All right, example 2 says a bacterial culture can be modeled using the formula P of n is equal to 7,500 times 2 to the power of n, where P of n is the population of bacteria after n growth periods. So first, how much of the bacteria are initially present? Well, based on our formula that we know, kind of giving it away there, but that's okay. That our initial population is going to be, well, the number beside the brackets or beside the exponent, so it's going to be 7,500. What is the growth rate? Well, if this part represents our growth rate, R represents our growth rate, and our equation is this, it's 2, well, 1 plus something has to be equal to 2. Whenever that something is going to be R. So 1 plus 1 is 2, so R is going to be 1. So what is the growth rate? The growth rate is 100%. If the bacteria culture doubles every 36 hours, how much bacteria is present after 2 days? Oops. All right, this question is a little bit funny. It depends on how you actually interpret the question. For the sake of this, I'm just going to make it really simple and just say we're going to assume that the bacteria, at exactly the 36th hour, they reproduce and double at the 36-hour mark. They don't do it continuously for 36 hours and then we just get the doubled amount. We're just going to assume they all kind of double up at the 36th hour. The main thing is we just have to see that these units are different and they should be the same. So we have to either convert this into 48 hours or make this into like 1.5 days if we wanted to. But for our sake, for our equation, if we have 7,500 as our initial amount and it doubles every 36 hours after 2 days, or how much is after 2 days? So if it doubles every 1.5 days, that's a 5, and it's been 2 days, well then it would only double once. So I would just do 7,500 times 2, again just to keep it simple, which of course I know how to do, I know the answer, but for some reason I gotta double check. Doesn't hurt to do that. Okay, and example 3 says, hoping to prevent extinction, 75 African bat-eared foxes were moved to an animal reserve in Africa. 5 years later, the population was observed to be 225. Determine the annual growth rate of the population over the 5 years. So again, my equation is this. What did they tell us on the question? Well, the initial amount that they put in was 75 of these foxes. What else do we know? We know after so many days, or sorry, after so many years, after 5 years, we have 225. If we know the number of years, that's going to be n, is 5. And they want us to figure out what the annual growth rate is, so we got to figure out what r is going to be. So just isolating variables, I'm going to put 225 here. Our initial amount is 75. 1 plus r to the power of 5. So I'm going to first divide both sides by 75. That way this goes away, and I'm just left with 1 plus r to the power of 5. 225 divided by 75 is 3. Now, I want to get rid of the exponent that's here. So, we said if I want to get rid of, if we want to get rid of something squared, we say we square root it. So, way back in earlier chapter 7, if I want to get rid of this, I'm going to take a fifth root here to cancel out that exponent. Whatever I do to one side, I do to both sides. These cancel out. I'm left with 1 plus r here. And the fifth root, I should maybe show that here. So I'm pressing 5 first. Then I want the second function of this orange part here, the x square root sign. So 5, fifth root of 3 is equal to this. I get 1.2457. Well, it's going to round that to 1.25. So I get 1.25 here. I want to isolate for r, so I'm going to move the 1 to the other side. I get r is equal to 1.25 minus 1. R is equal to 0.25. So the growth rate, growth rate is equal to 25%. So as long as we know this, we can, and we know enough of the variables, we can figure out other variables in this population equation, or this exponential growth equation, sorry. So thanks for your time.